Good morning, everyone, and welcome back to Math 115. So today's class, we're going to talk about section 1.4. What I want to note before we start is that 1.4, or today's lecture, is not on exam 1. Okay, so the exam is going to cover everything up to 1.3, okay? So let's say that's going to be A.1 through 1.3. I'll put that right there. So I believe you have you have 2 homework assignments today. Well, there's 2 homework assignments, but they're both really short. On 1.3 due today, so those are going to be one on like slope of a line and then parallel and perpendicular lines. So those are going to be due today at 11:59. If you need like an emergency extension, then just send me an email, but I'd like everyone to finish those homeworks before we have the exam on Wednesday. So speaking of that, the next assessment is going to be the exam. The first exam is going to be on Wednesday, and I think it counts for like 15% of your grade. So one thing that's different about college math to high school math is that exams are a lot more heavily weighted. Okay, so exams are definitely something that you want to spend some time studying for. I'd say, at least probably 4 to 6 hours at a minimum if you feel like you're already kind of like pretty well familiar with this material. So if you want to know how to study for exams, then you can check the syllabus. I have a section on the syllabus that details like a ton of different things that you can do that would be a productive use of your time when studying for an exam. And that is really the key to it, is you want to make sure that you're using your study time productively. That means not reinforcing stuff that you already know well, but finding the things that you don't understand and focusing on them and working on problems from that section or those sections, and then asking questions during office hours about those sections, and so on and so forth. So to that end, tomorrow we will have a review session in class. So what I usually do for the review session is I show up with some stuff prepared, but what I would rather do is hold basically a whole class-wide office hour. Okay, so you can come in and say, hey, I was working on this problem from the third homework and I didn't understand how I'm supposed to do it. Can you show us how to do it? And then I'll work that problem out on the board, and I'll give any like relevant comments or theory as we go along. So it would be really helpful if some students could come prepared with questions or things that they want to work on, even if it's something like you don't even have to necessarily go through all the homeworks and look for specific problems, but you could say, I didn't understand exponents. Can we go over exponents? That's something I can work with. So that would be helpful. But if not, then I'll prepare some practice problems for us to do, and I'll try to cover like, I don't know, a decent amount of different topics. So my office hours this week are again going to be Tuesday, Thursday, 2:30 to 4 in LeConte 439. My Tuesday office hours, let me just see a show of hands. Who's planning on coming to Tuesday office hours? Okay, so that's like a lot of people. So my office is kind of tiny, so I'll probably try to rent out a room in LeConte. So the room might change a little bit, but it should still be in LeConte. I'll send an email about that. If you can't come to my office hours, another great resource is the Math Tutoring Center in LeConte 102. So Monday, Tuesday, Wednesday, Thursday, you can go to LeConte 102 from 10 a.m. to 3 p.m. and receive free math tutoring from another graduate student. So that's somebody who already has an undergraduate degree in mathematics, is here to study mathematics at the PhD level. They'll be able to help you just as well as I could. Probably almost as well as I could. No, I'm just kidding. But anyways, no, they'll be able to help you really well, and they have a much wider schedule than I do. So that's a great option if you can't come to office hours and you can't find a time to schedule a meeting with me. By the way, if you sent me an email to schedule a meeting with me, talk with me after class today. I can't remember who you all are, but we'll talk. All right, that's all I wanted to say about the exam and studying for the exam. So are there any administrative questions before we start for the day? Yeah.
What's the math room?
Sorry?
Like what number is the math room?
The math room, it's LeConte 102. So it's on the first floor of the LeConte building. And there's like a plaque outside that says Tutoring Center.
Okay.
So you'll know when you're there. Any other questions before we start? Yeah.
Could we get the last quiz back so we can like review with it?
Oh, right. Yeah, I have that. Maybe I should have distributed that before class. I'll distribute that after class. Maybe you can come and get yours at the end. I'll have them in alphabetical order. So we'll pass those out at the end of class if you have time. Otherwise, I'll pass them out tomorrow before class. Thanks for reminding me about that. Okay. Any other administrative questions before we start? Yes?
Is the test in downstairs or is it up here? Or do you do it?
The test will be on Wednesday, so we'll be in this room.
Oh, is this room?
Yes, it'll be a 50-minute exam in this room. I'm actually not going to be here that day. A colleague of mine is going to be here to proctor the exam for me that day, but I'll give him the exam and he'll be able to answer any questions that you need. Yes?
So how many questions are on the exam?
So I don't have a number for that because I haven't written it yet, but maybe what I can say is that it'll be 2 to 3 times the length of a quiz. Well, I don't know. I mean, some quizzes will be 3 problems or 4 problems. You know, it depends, but my goal is not to pressure you for time. I will give a representative sampling. Obviously, I can't test you on everything we've learned so far. That's just way too much material. So I'm going to take a shotgun approach and just pick a handful of those topics at random. So you'll need to be prepared for everything. But, you know, there will be some samples of material. All of the homework problem, or all of the exam problems will be homework problems. So there won't be anything new to you on the exam that you haven't seen before. And my goal is to set it so that nobody really needs to, have more time. I think most people should be able to finish in like the 30 to 45 minute mark. But you'll have the full 50 minutes. Any other questions? I know there's always like a lot of anxiety before the first exam, but trust me, if you prepare well with the homework, you can't go wrong because you'll already know everything. All right, well, let's start for today. So today we are going to talk about functions, and it feels like I write finally here because it feels like we've been dancing around this topic for quite some time now. We've talked about solving quadratic equations, we've talked about linear equations, and all of these equations and stuff, and we've never really introduced functions and function notation and what is a function. So once we have talked about 1.4, the mathematical language is going to, I think, become a lot easier because otherwise I feel like I'm just dancing around this topic without being able to say anything about it because we haven't talked about it yet. So that's why I'm relieved. So let's talk about what a function is. Well, a function from a set x to a set y, so yes, that's right, set notation is not going anywhere. We have sets of numbers, and we say that a function takes a set of numbers x, and we map it to a new set of numbers y. And the new set of numbers y is going to have each element of y is going to be assigned to exactly one element. No, I said that the backwards way, sorry. What we are going to do is we are going to assign to each element of the domain x exactly one element of y, okay? So it's possible that we have multiple things in x that all map to the same thing in y. But what is not possible is for one thing in x to map to 2 different things in y, okay? So that's what functions are all about. So let's see an example of that in action. Okay, so here's a function that is mapping the set x of numbers 1, 2, 3, and 4 to the set y of numbers 5, 6, 7, and 8. Okay, so this function assigns to 1 the value 6, and it assigns to 2 the value 8. It assigns to 3 the value 6, and it assigns to 4 the value 5. Okay, so this is an example of a valid function, for it assigns to each element of x one and only one element in y. Okay, one and only one element in y. Okay, so here's an example of when that rule is violated. Okay, here's an example of that rule being violated. Okay, 4 goes to 8, sure. 3 goes to 7, fine. 2 goes to 7, fine. But here we have 1 being mapped to 5 and 6. Okay, so why is that bad for a function? Okay, well, here's why. A function should be, loosely speaking, consistent, right? So imagine if I had I'm going to scroll down for a second and introduce this conveyor belt idea really quickly. So imagine if I had a function which is like, okay, I live in a factory, and I have all these numbers floating around me, and I have certain machines which I can use to change numbers into different numbers, right? Okay, well, what I want is for this machine to be consistent in the sense that if I put the number 3 in, okay, then whatever number comes out, what should happen is if I put 3 in again, I should get the same number out once again, right? Because that would be what a useful machine does. I should be able to understand what the machine is going to do. If there's like a half chance that the machine puts out a 9 and a half chance that it puts out a number 8, then it's really hard for me to use this machine in a useful way because it's not consistent. But we'll talk more about that later. What we need to understand is that repeated y values are fine. Okay, for example, in example 1, we have 3 and 1 both mapped to 6. This is okay. Okay, no problem here. Repeated values in x, which we'll later come to know as the domain, okay, which map to separate values in the range, is going to be a big no-no for functions. Okay, so that's basically the one thing that distinguishes a function from a more general mathematical object, which we call a relation. Okay, so a relation could be either of these. They're both fine as a relation, but only one of them fits the description of a function. Okay, any questions so far? Okay, if not, then we'll move on. So I already kind of said this word, but let's talk about what the domain of a function is. Okay, well, it's fairly simple to define. We say that the domain of a function is the entire set x of inputs. Okay, so all of the numbers which I can plug into my function. Okay, all of the numbers which I can plug into my function. Okay, so in this example, which is the example from above, right, the domain is, of course, going to be a set, right? It's this entire set. Okay, so we're going to go back to using set notation again. Now, to use set notation to describe a bucket of numbers, which includes the numbers 1, 2, 3, and 4, but no other numbers, I'm going to do a squiggly, which, okay, technically speaking, it's supposed to be one of these, okay? But I never draw them like that because, I don't know, my hand doesn't do that. So I'm going to put in the numbers 1, 2, 3, and 4. And then let's do another one of those. Okay, so that's how it's supposed to happen. From here on, I'm going to do squigglies. And then that is the domain of this function, is the collection of numbers which are okay as inputs for the function. Sometimes the domain will be specified. In this case, the domain is specified. in the problem. We'll talk later about what to do when the domain is needs to be inferred by you. Okay, so that's the domain. Yes?
Why is it like 1, 2, 3, 4 and not like 1, 4?
Why is it 1, 2, 3, 4 and not something like 1, 4?
Yeah.
Like this?
Yeah.
Okay, can anyone answer this question? Why do we write the domain like this? The numbers 1, 2, 3, 4 instead of like this, 1, comma 4. Gavin.
That's talking about specifically like 1 and 4 instead of like the entire set.
You're dancing around that, Ashley.
Because the top example includes like all values between those numbers, so decimals as well.
Very good. Ashley hit the nail on the head. This set of numbers contains every number which is larger than 1 and smaller than 4, inclusive. What that means is that this set has numbers like 2.5 in it, right? 2.5 is a number in this bucket because we throw in all the numbers which are between 1 and 4, right? But what's the problem here? There's no 2.5 in the domain. Okay, so if I write it like this is a set which includes the numbers 1, 2, 3, and 4, but it also includes a bunch of other numbers which aren't in the domain, like 2.5 or 0.1 or any number in between there, right? Does that answer your question? Okay, so what we want to do is, in this case, we only have 4 numbers. So I write them as a comma-separated list because if I have a finite amount of numbers, it's easy for me to just write them all down. Is that clear? Any other questions about this notation for a set of finite numbers? Okay, doesn't seem like it. So let's talk about the range. Well, we already talked about x, so now we're going to talk about y, right? So the range is the word that we use to describe the subset. Okay, so now we're not talking about the set, we're talking about the subset. That means it's a subcollection of numbers, right? The subset of y to which an element of x has been assigned. Okay, so what this means is, loosely speaking, we're going to talk about the set of all possible outputs. Okay, so now we look at y here, and here's the thing. 4 goes to 5, 1 goes to 6, 3 goes to 6, 2 goes to 8. But there's a number in y which nothing in x actually maps to, right? It's the number 7. It doesn't actually get hit by anything in x, right? So that's a number which we would say is not in the range. Okay, we would say 7 is not in the range because it's not an element to which an element of x has been assigned. There's no element of x which is assigned to the number 7. Okay, so therefore, the number 7, even though it is an element of y, it's not going to be an element of the range. The range is going to be the subset of y. The subset of y to which an element of x is mapped to. So what am I going to get here? I'm going to do some squigglies here. And then another squiggly on the right. And then what numbers should I put in the range? 5, 6. Any others? And 8. How about 7? No, I'm not going to put 7 in because 7 is not mapped to by any element in x. Okay, so this is an example of domain and range where we have a finite number of elements x in the domain and a finite number of elements y, or elements of y, which are in the range. Any questions on how we defined the domain and range and how we found them for this particular example? All right, then let's move on. So now I'm going to talk about function notation. Okay, so what is function notation? Function notation is just a special way that we write things, okay? So all the time, you may not realize it, but there's been someone like 800 years ago or 2,000 years ago who decided how we're all going to write stuff down, right? So there's no reason that I should say f of x and not something like f sub x or something like f to the x or something like, you know, whatever, right? There's a decision to be made in terms of how we write things down. So what I mean when I say notation is I'm going to show you what we write, and then I'm going to tell you what it means when I write that, okay? So this colon equals sign here is a mathematical symbol which we use to say is defined to be, okay? Is defined to be. So when I write f of x, this is defined to be the value given by plugging x, the number x, into the function f. So the function is called f. We plug in a number x, and then via our conveyor belt, right? Via our conveyor belt, we plug in a number, x, into the function f, and out pops something which we call f of x. Okay? Which we call f of x. So this is function notation. So the terminology that we use to go along with this is sometimes I'll say something like f of x, or f evaluated at x, or f at x. I rarely hear people say this one, but if you say that, that's fine. Any questions on the notation? Okay, that's just how we write things. So let's see an example of how this notation is used. So in the context of this function here, which again is the same as before, then f of 1 is supposed to be the value which we get when we plug 1 into the function. Now when I say we plug 1 into the function, what I mean is we check the domain, we look for the number 1, and we look to see where does that number get assigned. And that assignment, okay, is what we call f of 1, which in this case is 6. Okay, so we look for 1 in the domain, we see what it gets mapped to, in this case it's 6, therefore f of 1 is equal to 6. So how would I do f of 4? What would I get if I did f of 4? I'd get 5, right? Because 4 is mapped to 5. So the element 5 in y to which 4 is mapped is what we call f of 4. Okay, so two different, in the context of this example, you know, when I say equals to, what I mean is that these two things on the left-hand side and the right-hand side are the same, right? So whether I write f of 1 or whether I write 6, it's like I'm saying the same thing. It's like I've written down the number 6 in English and in Spanish, okay? English and in Spanish. So they mean the same exact thing, it's just a different way of writing them. All right. Any questions on function notation so far? Okay, then let's make it a little more complicated. Okay, so this is another representation, by the way. Okay, so, you know, how I actually wrote this down is subjective, right? You can do it in many different ways. So this is one way that's popular that people like to use when there's a finite domain, and you can just draw the arrows of what everything's going to. It's pretty clear and easy to see, but there's a number of different ways that we could represent that information, okay? So another thing that we could do is, for example, instead of writing this circle and this circle, putting the numbers inside and then drawing arrows, is we can communicate the same information by listing ordered pairs. Okay, we can list 4 ordered pairs, one for each of the elements in the domain. So the ordered pair is going to be, the first value is going to be the element of the domain, and then the second value of the ordered pair is going to be the element of the range to which that element of the domain is mapped under the function f. Okay, so for this example, we can recreate this information by saying, well, what this says is 1 goes to 6, 2 goes to 8, 3 goes to 6, 4 goes to 5. We can say the same thing using ordered pairs by saying 1 goes to 6, 2 goes to 8, 3 goes to 6, and 4 goes to 5. So this is another way that you can write down what's going on with a function. Another way that we could write down what's going on with a function is with a table, okay? We could do a table where on one side I'm going to put x, and on the other side I'm going to put f of x, okay? So these correspond directly across, directly across, directly across. So 1 goes to 6, 2 goes to 8, 3 goes to 6, and 4 goes to 5 can be explained using this table. So two different ways that we can see things. Sometimes I'll do the circles, sometimes I'll do the ordered pairs, sometimes I'll do the table or whatever. Okay, so that's just two different ways that you can represent a function that I want you to be aware of. So now let's talk about the difference between a relation and a function. I already kind of touched on this, but here's what I want to communicate. The one important rule about functions, let me scroll back up to the top. What was the one important rule about functions? Well, it's not just from a set x to a set y. What we also need is that we assign to each element of the domain exactly one element of the range, and not more than one. So not 0, not 2, not any other number, just 1. And only 1. Okay, so what does that mean in terms of looking at a table? Okay, to determine the difference between a relation and a function, okay, we can look at the tables here. So what's the problem with this relation here that is causing it to not qualify as a function? What's the problem with this relation? Yes, I have one x value, -1. The relation maps -1 to 1, and also -1 to 2. Okay, also -1 to 2. So we have one x value going to multiple different y values. This is the problem. Okay, this is the problem. All right. So why then is the one on the right-hand side still a function? I've got a multiple. I've got -1 here, and I've got -1 here. I thought that we are not allowed to have extra x values. Why is this one okay? Yeah, because in both circumstances, I get back out the same number, 1. So really, it's kind of I don't know if tautological is the right word, but it's completely unnecessary to rewrite this because the information's already there. I already know what -1 goes to. Why are you writing it twice? So it's kind of weird that you would write this twice, but it's okay as long as they both go to the same element y in the range. Okay? So the problem is when we have x values going to different y values. Two of the same x values going to different y values. Okay, so that's the difference between a relation and a function. So for example, on your homework, you'll probably get a table, and they'll ask you, does the table represent a function? And you'll say yes or no, based on whether there are repeated x values going to different y values. Or maybe they'll give you a list of ordered pairs, and they'll say, does the list of ordered pairs represent a function or not a function? And you'll say yes or no based on whether there are repeated x values going to different y values. Or they'll give you circles, and they'll say, does this represent a function or not? And you'll have to say yes or no based on whether there are repeated x values going to different y values. That's an example of what you might see on the homework. Okay, so let's talk about the graph of a function. So we already talked about the graph of a relation, right? The graph of a relation was all of the ordered pairs x, y, which satisfy, not the graph of a relation, I'm sorry. We talked about the graph of an equation. The graph of an equation was all ordered pairs x comma y which make the equation true. So now what we're going to do is we're going to graph all of the points x comma f of x. Okay. We're going to graph all of the points x comma f of x. Okay. That's what we're going to do. So I'm going to take a certain amount of values x here, and I'm going to look at all of their values under the function f. Sometimes I'll say under the function f, x takes the value 6, or x equals 1 takes the value 6 under the function f. Okay, so that's another terminology. So what do I mean here is that the function f, just like how I showed it upstairs, right? 1 goes to 6, right? So I'm going to re-communicate this information in terms of a table. I've got the points x and f of x, and I'm going to make 4 points. The first point is going to be the point 1 comma 6. So that one is shown here, right? It's 1 to the right and 6 up. Then 2 comma 8, I go 2 to the right and 8 up, okay? And then 3 comma 6, I go 3 to the right and 6 up. And then 4 comma 5, I go 4 to the right and 5 up. Okay, so this is the graph of a function, is the collection of ordered pairs x comma f of x, okay, where x is in the domain. Another way we could say that is that x is in capital X. Okay, so that is one thing I want to distinguish, is that when we're talking about the set x of all the domain, okay, so this set here of all of these numbers, we use a capital X, okay? When I'm talking about a specific member of the domain, like 2, then I'll use a little x. It can be kind of hard to tell sometimes which one I'm doing, so I'll try to say it out loud. Okay, any questions about the graph of a function? Is this pretty familiar? Can I have like a show of thumbs if you feel familiar with this, and thumbs down if you haven't seen this very much before? Okay, I had a feeling it would be mostly review. All right, so let's talk about functions defined by equations. Okay, so sometimes we can define a function by an equation. So say we started with the equation y equals x squared, okay? Then we know how to graph this equation. We know what sorts of ordered pairs make the equation true or not true. So one of the things that we can do is we can say, well, what if I had a function whose output, if I plug in x, is going to be y, using this equation y equals x squared. Okay, then I could write y equals f of x equals x squared. And now I have a rule of, okay, you tell me what x is, and I'll tell you what f of x is. Okay? And what I'm going to do each time you tell me an x value is I'm going to take that number and square it in my head, and I'm going to say it back. Okay? Or I'm going to take my machine, and I'm going to take the number which you give me, and I'm going to plug it into the machine. And this machine has a specific job. What is the job of the machine? It's to take that number and square it, and then spit it back out. Okay, take the number and square it, and then spit it back out. Okay. So this is a function defined by an equation. So I'll also sometimes call this a function rule. Function rule. Okay, tells us what to do with a given input. Okay, so it's a set of directions or a set of blueprints, or if you want, it's the manual for this machine. It tells you what it's going to do. Okay, so that's functions defined by equations. So let's talk about how to evaluate a function which is defined by an equation. Okay, so before, how did we evaluate a function? What we did was, if we wanted to know what is f of 1, we looked at the table and we saw, aha, 1 is going to 6. So that's what f of 1 is going to be. Now, what are we going to do if we don't have a table of values, or if we don't have a collection of values? We just have a rule which says that f of x is given by this function rule? Well, what we're going to do is we're going to take, if we want to evaluate something like f of 2, we're going to take that number, 2, and we're going to plug it in for x, okay? So I'm going to put a 2 in everywhere I see an x, okay? I'm going to put a 2 in everywhere I see an x. So for this example, f of 2 is going to be equal to 2 squared minus 6 times 2 plus 8. And I will get 4 minus 12 plus 8, which I think is 0, right? 4 minus 12 plus 8, that's 0. Okay, so this is how we evaluate a function. So f evaluated at 2 or f of 2 is equal to 0. Okay, that's the output that I get. Okay, now let's do another one. Let's try f of negative 2. What will I do in this case? Okay, I'm going to show you an example, and I'm going to do something wrong. I'm going to let you know beforehand I'm going to do something wrong. So I want you to think as I go along about how I might have made a mistake here. Well, f of negative 2, I'm going to put a negative 2 in for x everywhere I see it. So I get negative 2 squared minus 6 times negative 2 plus 8. And therefore, that's equal to negative 4. Well, the negatives here cancel out, so I get a plus 12 and then a plus 8. So this should be equal to 20 minus 4, which is 16. But I made a mistake here. Does everyone see where the mistake was? Okay, I'm seeing a lot of nodding. Where was my mistake? In the square. Okay? What went wrong here?
Negative 2 is
Right. So the problem is I wrote it down a little bit incorrectly. Okay, what I'm supposed to do is I'm supposed to plug in negative 2 for x. So I'm supposed to take whatever that number is and square it, okay? Which isn't exactly what I wrote down here. What I wrote down here is negative 2 squared, which is there's a big difference between negative 2 squared and negative 2 squared, okay? So what I should do is always, 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 always plug with parentheses. Okay, so what I like to do is I'll put a 2 here like so, and I'll put a negative 2 like this, and I'll put a negative 2 like this, so that it's clear how I'm going to keep track of all the negative signs. Okay, so always, always plug with parentheses. It's easy, PWP. Okay, so what should it have been? It should have been positive 4. Plus 12 plus 8 is not 16, it's 24. So that's evaluating a function. We just plug in the number with our parentheses everywhere we see an x. Any questions on this one? Okay, it doesn't seem like there's any questions. So now let's talk about something a little more complicated. And I say it's a little more complicated because every time I teach this class, and also every time I teach 141 or 142 or 122, I have a lot of students who struggle with understanding how to determine what is the domain of a function with a rule. Okay, what is the domain of a function with a rule? Okay, so this is probably the most important part of today's lecture. So when the domain is unspecified, okay, so if they give us a rule like f of x equals x squared or something like that, so they don't tell us what the domain is. They don't say x is between 0 and 1. If they say x is between 0 and 1, then the domain has been specified, right? But if they don't write anything about x, then we are supposed to infer what is the domain, okay? We're supposed to infer what is the domain. So what we do is the following. We collectively agree, actually you don't agree, it's more like mathematicians a while ago agreed, that the domain of the function is going to be, quote unquote, the largest, okay, the biggest possible set of numbers which result in a real number output. Okay, so all of the real numbers which I can plug in and get a real number as an output, that is going to be the domain of my function. So let's do several examples here. Can I move down on the screen? Okay, 1 second. Okay, so we want the largest set of real numbers which result in real number outputs. Okay, I'm going to move down now. So, for example, if we want to find the domain of a function like f of x equals 1 over 1 minus x squared, okay, the complicated thing about finding the domain is you have to think about what are all the possible things that I can plug in for x that is going to make this equation okay. Okay, we've got to think about all the things that we can plug in for x that is going to make this function okay. Okay, so the easier thing to think about, in my opinion, is what numbers could I plug in for x that are going to cause a massive problem for this fraction? Namely 1 and negative 1, right? If I plug in 1, why does that violate this? Why can I not plug in the real number 1 and get a real number as an output? The reason is because if I plug in 1, I get 1 over 1 minus 1, which is 1 over 0, which is undefined. I.e., it's not a real number. Not a real number output. Therefore, 1 is not in the domain. And neither is negative 1 for the same reason. Right? Negative 1 times negative 1 is 1. 1 minus 1 is 0. Same reason. Okay, so now what we want to do is describe the largest set of real numbers which I can plug in to this function and get a real number as an output. Are there any other numbers that are going to cause this thing to blow up completely? No, right? Because that's the only thing we are worried about in this case is having a 0 in the denominator, right? Having a 0 in the denominator. So the way we're going to describe the set of the x, which is the domain, is going to be equal to the collection of all numbers which aren't 1 or negative 1. How can I write that down using interval notation? Using interval notation, I want to include all real numbers that aren't negative 1 or 1. Well, I'm going to need 2 unions, right, to do it. How should I start? Negative infinity up to what? 1? Negative 1. And should I have a bracket or a parentheses? Why a parentheses and not a bracket? Can you explain? Because negative 1 is not in the domain, right? We just determined negative 1 is not in the domain. So we should not include it. We should exclude it. Okay, now what comes next? Negative 1 to 1, right? I can also do all of the numbers between negative 1 and 1. It's fine for me to plug in 0, right? I can do 1 over 1 minus 0. That's fine. 1 over 1, right? Or any other number in between negative 1 and 1. And the last one is, of course, going to go from 1 to infinity. Okay, so this is how you could describe this domain. Okay, or if you want, you could say x is not equal to 1 or negative 1. And x is a real number otherwise. Okay, if you say it like this, then you're saying, okay, x is a real number and x is not 1 or 1. 1 or negative 1. That's another way you could write it. But this is how we would write it using interval notation. Okay, any questions on that example? I think that's definitely the hardest thing we've done today. Okay, let's talk about the range. Actually, before we talk about the range, what I want to do is I want to add a page here and say something else really quickly. So I want to tell you what are the things that you need to watch out for. So, things to watch out for. When finding domain. First, no dividing by 0. Second, no square roots of negative numbers. Actually, no even-powered roots of negative numbers, right? No even-powered roots of negative numbers. And, yeah, that's pretty much it. That's what you want to watch out for when you're trying to establish the domain, is you want to make sure you think about all the numbers which could possibly cause you to divide by 0 or cause you to take an even-powered root of a negative number. Okay, so let's talk about the range now. Okay, the range is of course going to be all of the possible outputs from an input in the domain. Okay, and this one is a little bit trickier to see, okay? You have to think in a little bit of an abstract way here to see what possible outputs could I get when I apply this function rule to all of the numbers in the domain. Okay, so in this problem, what do they tell us? They tell us what is the function rule, and they also give us a domain, okay? So we don't have to do all that work to figure out what it is, right? They tell us what the domain is. It's all the numbers between 3 and 5. And what I am supposed to do is describe all possible outputs when plugging in a number which is between 3 and 5, including 3 and 5, right? So in this case, it's helpful a lot of the times if you know how to draw the graph of the function. It'll be extremely useful in finding out what the range is. So let's draw what is the domain. Well, the domain here, 3, 5, can be seen here, 3 to 5, right? And what does the function x squared look like? It looks like a parabola, right? Okay, so when we're thinking here, we want to think about, okay, what are the possible numbers which I could get if I plugged in a number between 3 and 5? Well, we're squaring that number, right? So the smallest possible number that I'm going to get is going to be when I plug in the smallest possible number that I have in the domain, right? Smallest possible number that I have in the domain. So in that case, the smallest is going to be 3, right? That's going to be my, not 3, but 9, excuse me, right? That's what I get when I plug in 3. And what do I get when I plug in 5? 25, right? So here we can see the domain is 3 to 5, and the range is going to be all of the possible outputs which I could get if I plugged in a number which is between 3 and 5, which is going to be one of the numbers between 9 and 25. So in this case, the range is going to be equal to the set, or the interval, 9, 25. Including 9, because if I plug in 3, I get 9, and including 25, because if I plug in 5, I get 25. And I can get all the other numbers in between, right? For example, 24.99 is equal to the square root of 24.99, which is something squared, right? So this is the point in the domain, and this is the point in the range. Okay, so that's how we find the range here for this problem. And I don't want us to talk about the vertical line test, so let's stop there for today. Just a reminder, this will not be on the exam tomorrow, or on Wednesday. Oh yeah, come pick up your quiz if you want to get a quiz here. What's your last name, Sarah? Or Sully?
Hammond.
Hammond? Here you go. Okay, maybe this is going to be easier if I break this between some groups here.
Oh, hey. Have a good day. Like tomorrow.
Yeah, that's fine. All right, there's a handful of packets there.